Yeah, so thanks, Max, for the nice introduction. And yeah, today my talk is going to present you many of the results that we obtained in the pre-crime project, but what I would like to focus more is not really the technical results, but the methodological aspects that we discovered along the way. I think that there's a number of pitfalls in doing deep learning testing that we discovered. Some of them we were able to avoid, so I think it's interesting to share them with you. Some of them we didn't. I think they are open challenges, and if we want to make progress in this area, I think it's good to have some reflections on such open issues. So as Max said, the NERC project is a great thing. In particular, it gives you the opportunity to create a quite big research team. Here you can see their faces. I had the privilege to work with 4 fantastic postdocs and 4 fantastic PhD students. The overall idea behind pre-crime took inspiration from science fiction. From Minority Report, you might know the novel or the movie, where there's the pre-crime agency that tries to arrest criminals before they commit any crime. And you might, discuss whether this is a utopia or a dystopia, but what we wanted to do in the translation to software testing is to test systems that operate possibly in unexpected conditions where it's important to anticipate failures before they happen. So we want to identify the conditions that might lead to unexpected execution and possibly eventually trigger failures of the system. So when we started around 5 years ago, in 2018, we looked around and considered what could be a possibly interesting application domain for the techniques that we were to develop. And there was an emerging field, which was deep neural networks. It was not really emerging, it was exploding, literally, because it was achieving human competitive and even superhuman performance on many difficult tasks, like playing chess, performing processing of images, which previously was done with other statistical techniques, but eventually, if you look at the ImageNet competition, neural networks were always the winners. And then if you look at Kaggle, there's a number of tasks and competitions on which the winners are always neural networks. Sentiment analysis, speech recognition, audio tagging, object detection, all these complex tasks can be carried out today successfully thanks to neural networks. So they were really a game changer, and they have started being integrated into very complex applications like self-driving cars, autonomous drones. We all know automated generation of code from descriptions, automated translation from one language to another. This is a pretty classical and historical application of neural networks, and more recently, conversational agents. So, a number of pretty interesting complex applications. When I say complex, I mean that they operate in complex domains where the space of the possible input scenarios is so big that it's impossible to think of sampling it in a representative way, and you have to consider that unexpected execution conditions might happen at runtime. So, why not taking the techniques we are used to, we developed in this community, and applying them to neural networks? They might work and give us dependable systems. Unfortunately, it's not like that. So let's spend a bit of time discussing the programming model behind neural networks. It's pretty different and unique as compared to traditional software. So let's take an example. On the left, you see a neural network that takes in input the pixels of an image. In this case, it's the image of a semaphore, and the output is 2 neurons. So the first neuron corresponds to the classification of the image as an is red semaphore, and the other is the opposite. So the semaphore is not red. So here, the 2 output neurons have 2 activations, and the highest activation is for the is red flag. So this image is classified as a red semaphore. So the neural network is taking a decision. It's deciding that this is actually a red semaphore. But if you look at the code shown on the right, there's no decision logic, no single branching point. The code is, very boring. It's just a plain sequence of instructions that stack layers of neurons one after the other, trains them, and finally makes a prediction, and the prediction is 0.94 is red. So where is the decision logic? How can we test it if it's not in the code? And the answer is that it's all data-driven. Basically, the input data is represented as a numeric vector that is propagated inside the network through the weights that are determined through training, and eventually the output determines the decision. So this is pretty different from what we are used to, which changes a lot of the things in the testing fundamentals. So first thing, the very notion of a bug is going to be different. So let's assume for a moment that given this semaphore image, the output of the neural network is 0.1, 0.9. So the second neuron is the highest, which means the semaphore is not red. So is this a bug? How many of you believe this is a bug? Please raise your hand. Don't see very much. A few. Okay, how many believe it's not a bug? Please raise your hand. Okay, so I guess you are already confused, which is a good sign because most of you didn't answer. I was also confused when I started. So let's consider, to answer this question, the kind of contract that we stipulate with a neural network. And here we see another important major difference as compared to traditional software. So on the right, you see some example of traditional software. And a contract with a traditional software component is a precondition, implies a postcondition. So if the code implements the computation of the square root, the possible contract is if the input x is greater than or equal to 0, then the output y multiplied by itself will give us approximately x. This is the kind of contract that we're used to. What contract, if we want to integrate a neural network component into our system, what contract can we stipulate? It's a very different one. It's a probabilistic contract. All we know is that the accuracy, which is the probability of a correct prediction, as measured on an independent test set, is, for instance, 0.99. That's the accuracy. So back to the question, is this a bug? Well, if this example of semaphore image belongs to the 1% that is expected not to be classified correctly, then it's fine that it's misclassified and it's part of the contract. There is no contract violation. So the contract is actually respected. Can we expect to achieve 100% of accuracy or prediction, and such that we go back to the more traditional, more usual deterministic notion of a bug? Unfortunately not. As we will see, not only on the test data, it's unrealistic if we are operating in a complex domain such as the ones that I showed you. It's unrealistic to expect 100% accuracy, but when we move from the test data to the production data, there's a phenomenon that is known as development to production data shift, which typically decreases the accuracy even further. So this means we have to live with a programming model which is data-driven and with contracts that are probabilistic. So what happens to testing? Is it going to be the same or different? And if we summarize what happens in testing, well, we have a program traditionally with possibly one or more faults, and we want to select test inputs such that if we execute those, we violate some oracles that generate failures, and these failures point to opportunities for repairing the program. This is the standard testing frameworks that we all are used to, and the goal of testing in a traditional setting can be stated as we want to repair faults exposed by choosing inputs whose execution violates oracles. Great. So, as we have seen, a number of things change when we have a neural network under test. So, in the rest of my talk, I will reconsider each of the elements in this testing framework, and I will adapt them, trying to formulate or to propose a new testing framework that works for deep learning components. So I will start with talking about deep learning faults and failures. Are they different? How do we consider them? Then I will talk about the inputs. How do we generate them? How do we prioritize them? And then I will talk about oracles. So first of all, faults. This was our first important question. The code is not necessarily the only place where we can expect faults to happen. There are other elements that affect the behavior of a neural network. most notably the training process with all the elements that intervene in the training process. If we apply the IEEE standard definition of fault, which is a mistake in a computer program, in an incorrect step, doesn't work. So we needed to start the project a better definition of what a fault is, a better understanding, not only a definition. To achieve that, we conducted an empirical investigation, which consisted of some software repository mining. We mined Stack Overflow and GitHub, looking for discussions, commits, and issues and pull requests about deep learning faults, and we interviewed 20 researchers and practitioners. Then we labeled all these amount of data that we collected, and we organized those labels into a taxonomy. And then we have validated the taxonomy on 21 researchers and practitioners. And if we zoom into the taxonomy, of course, I don't have the time today to present it. As I said, I will not focus so much on the results, more on the methodology. But if we zoom into it, we can discover a number of faults that are completely new and completely unique to deep learning models and neural networks. For instance, a neural network might have an unsatisfactory behavior because it has missing or wrong layers, or the properties of layers are incorrect, or some activation function is chosen incorrectly. Or if we look at the training faults, those affecting the training process, well, the hyperparameters are very important. A suboptimal learning rate or batch size is often a reason for bad performance of a neural network. The choice of the loss function, the split into validation, training, and test set is quite important. Training data is an important source of faults, and a lot of faults are due to wrong labels that are attributed manually to part of the training data or to unbalanced training data, just to give you a few examples. So there's a whole set of faults that are unique to deep learning and that need to be handled properly, and the first thing we wanted to do to handle them properly was to be able to simulate them into existing neural networks. So if we want to know if a test generator is good at exposing faults, we need faults. But finding faults in the wild is difficult. I will talk more about it for neural networks. So in order to simulate them, since we had a taxonomy, we developed a mutation analysis tool, DeepCrime, which takes in input all the elements that define the behavior of a deep learning component, so the training set, but also the network architecture and the hyperparameters, and the DeepCrime modifies them before training the neural network, such as to produce a neural network that has a lower accuracy. And then these can be useful for many purposes. So here you can have a quick look at the mutation operators that we implemented. They map pretty well to the taxonomy that I described. So some mutation operators are about the training data. We can change the labels of the training data, remove part of that, and so on. Some regard the hyperparameters, changing the batch size or decreasing the learning rate, some the activation functions. So for each leaf in the taxonomy, we try to define a mutation operator, and now that we have them, we can simulate faults that is useful to decide if a test set is adequate first, and to compare test input generators. If we want to know if a test suite or a test generator is a good one, we can check if it can discriminate between an original neural network and one that contains faults injected by DeepCrime. It was also used as a benchmark for repair tools. I will talk more about it later, and to assess the prioritization techniques. Good, so we know now a little bit more about faults in deep neural networks. What about failures? So we have a fault, we can inject it, but then this manifests itself as a failure. So we can recognize failures. Here there's not so much of a mismatch with standard definitions, but counting failures is very tricky. So on the top you see 6 images of a self-driving car that goes out of bound. And this happens on some tracks generated automatically by some test generator. On the bottom, you see some 5 digits that are misclassified as 6. So one might be tempted to say these are 6 failures at the top and 5 failures at the bottom. This way of counting, however, is subject, is actually a pitfall, is pretty tricky and might lead to inflating the number of failures that are exposed by a particular technique, and it might also lead to an improper estimate of the reliability or the accuracy of the system. If you look, for instance, at the 3 examples for a self-driving car, the 3 on the left, they look all very similar. And in reality, once you discover for a neural network a failing scenario, it's pretty simple to generate 1,000 of them. Just changing a little bit of pixels that are irrelevant for the decision, and then you get 1,000 failures. So you can have one testing technique that produces 1,000 failures, and another one that produces only 3. Which of the 2 is better? Depends, which failures are discovered. And here the notion of unicity or uniqueness of failures is critical, and as I say here, diversity matters. So we try to address this problem by proposing feature maps. Feature maps are a way to characterize failures based on the feature combinations that they exercise. So in a feature map, each failure is mapped to a cell that represents a specific combination of features that define the uniqueness of that failure compared to the other ones. So back to my previous question, we have 2 testing techniques, one exposing 1,000 failures and the other one 3. Which of the 2 is better? Well, if we map those failures into feature maps, and we discover that the 1,000 go into one cell and the 3 go into 3 different cells, then maybe the second technique is better. And this is one of the pitfalls that is quite widespread, especially in the early works in the field, and is something I definitely want to warn you about. Good, so we know what faults are, we have seen how to count failures. What about repairing a neural network? So once we have exposed the failure, we want to repair it. So you already would agree with me that repairing is going to be different from traditional repair. We are not going to change much the code. But the thing is even simpler. Since we have a taxonomy of the faults that represent ways in which faults are introduced in neural networks, what we can do is we can take the mutation operators and revert them. The inverse of each mutation operators represent one way to fix a fault. So if you take the training data category, instead of changing the labels of the training data to make them wrong, we fix them to make them right. Or we can augment the training data with more data, or we can rebalance an unbalanced training set. If we talk about hyperparameters, instead of changing the batch size or decreasing or increasing the learning rate to make it worse, we can fine-tune it to make it better. So what we discovered is that we already had a machinery of repair operators available. So the next question was, how do we apply them to a neural network? And what we found is that people had already considered this problem, in particular in the software engineering community. Here I'm citing an ICSE 21 paper. There have been interesting developments. It's not the only paper that does this. This is called AutoTrainer. But we also discovered that in parallel to us, the machine learning community has spent a lot of effort on deep learning repair. There's an entire field which is called AutoML that tries to automate machine learning tasks, among which what we call deep learning repair, unfortunately, they don't call it like that. For them, this is hyperparameter tuning. So the 2 things don't match. The 2 developments are in parallel. There's no comparison of the 2 approaches, and they are also quite different conceptually. So if you look at AutoTrainer, the approach is rule-based. It monitors the training process and looks for symptoms of a bad training process, and every symptom is associated to a solution. The solution is an inverse of one of the mutation operators that we have seen. So, for instance, add a batch normalization layer, change the activation function, and so on. So it's a rule-based system with symptoms associated with possible candidate solutions. In the ML community, instead, the most promising, most recent approaches are based on Bayesian optimization, which means they sample the hyperparameter space, which we would call the space of the possible repair operations. And then what they do is they fit a surrogate model, which is able to predict the performance of the neural network for a given choice of the configuration of the repair operators, and then it samples the next hyperparameter configuration to trying to balance exploitation and exploration. On one hand, you want to choose the configuration that gives the highest accuracy, the highest improvement of the performance of the neural network. On the other hand, what you want to do is you want to explore at large the space of the repair actions. So with this strategy, you sample the hyperparameters and then you train the model. And the reason why you have this loop with a surrogate model in it is because in this repair business, the key cost is training a model. Whenever you want to try a repair, you have to train a model and check its performance. So to save training time, it's important to have a surrogate model in the middle. So that was great because we had these two alternatives to do repair, but as I said, they were developed independently, so what we want to do was to compare them empirically and see which is the best, or in which cases one is better than the other. And what we also discovered is that if you want to do this kind of comparison, the thing is not so easy. Because if you look at the individual benchmarks that are proposed also by the two communities, they are quite biased and specific to the approach, to the assumptions that they make. It's difficult to get an independent benchmark of real faults on which to test them. It's also difficult to get real faults. In many papers in deep learning testing, you will see that results are computed on real faults, but you have to be careful about that. If you look deeper into the replication packages, you often discover that these are considered real benchmarks just because they have been taken from GitHub. But often in GitHub you find student projects where for instance, the feature vectors are generated randomly. The labels are generated randomly. There's nothing to learn because you can't learn any interesting function from random data, but it's often reported as a real data set. So to make a fair comparison, we defined our own benchmark of real faults. It's a small one for now because it's a lot of work. And then we also took advantage of deep crime to test these techniques on artificially injected faults. And here you see the results. We compared a random choice of repair operations with AutoTrainer, Hibo, and Bob. Hibo and Bob are recent representative of the hyperparameter optimization techniques. These techniques are compared on the improvement rate, which is the amount of improvement in some performance metric like accuracy, compared to the improvement that you have between the fixed version of the neural network and the faulty one. So if you achieve 100% or 1, basically the automated repair is equally effective as the manually defined fix. You can even achieve more than 1 improvement rate. It can be occasionally greater than 1 if you find a better repair. And here you see, for each technique, you see 3 box plots. They are at increasing training budget. Here the training budget, as I said, is the key parameter. We are increasing it from 10 to 20 to 50. What we discovered is that there's no clear winner, and the overall performance of these techniques is quite poor. On some categories of faults, they work fine. On others, they work very poorly. So the overall conclusion of this investigation is that neither community has solved the problem. It's still open. If you are a PhD student, I guess it's an interesting research area to consider. So we discussed the first component of a testing framework for deep learning elements, for deep neural networks, and I want to give you a few takeaway messages about it. So first of all, we discussed that deep learning faults affect the data, the model architecture, the hyperparameters, not just the code. The code is quite irrelevant for them. Then the other important message I want to give you is failure counting. Uniqueness, diversity has to be characterized properly if you want to get numbers that make sense. And the third takeaway message is about the repair operations and automated repair of neural networks, which is basically an unexplored field regardless of the existing work, because there's a lot of margin of improvement. The second element of the framework that I'm going to construct step by step is about inputs and input generation. How can we generate inputs? So we developed one technique called Deep Janus that generates input at the frontier of the behavior of a neural network. What is the frontier? The frontier is defined as a pair of inputs that are close to each other, such that on one of them the behavior is correct, and on the other one it is incorrect. Why is the frontier interesting? Well, because this represents the point where a neural network starts to misbehave. Of course, if you get far from the input domain where the neural network behaves properly, you will find misbehaviors, but the interesting points are at the frontier because we want to know if these points belong to the validity domain or not. If the first input that you get on which you have a misbehavior is within the validity domain, then definitely we have something critical which might deserve further inspection and possibly attempts of improvement of the neural network. If the only misbehaving inputs are really impossible to classify or categorize, even for a human, because they are outside of the validity domain, then we are fine. Then we can say the neural network has acceptable performance. So we developed this, and in this development we recognized immediately that the validity or the validity domain for an input is really a critically important aspect. In traditional software, we assess the validity of an input with a precondition. So if we have a square root function, we have an assertion saying x must be greater than or equal to 0. That's a precondition. If you look at the digit recognition function, you will get a neural network, make a prediction, and there is no validity check. Which means basically that whatever is the input, you get an output. So if you pass a digit A, a handwritten digit A, to a neural network that performs digit recognition, you might get 4 as a classification, which makes no sense because the input is invalid. This first example of invalidity is quite interesting because for us humans, it's clear that an A is an invalid input, but if you look at the features, at the visual, graphical features of this input, they match pretty well those of a digit. So if we want to automate the validity check, for this example, it's not easy. The second example is clearly not a valid input. It's classified as a 5, but it's clearly out of bound, out of distribution, sorry. The third is the most difficult to classify as invalid because it's ambiguous. It's something between a 1 and a 7. So probably if I ask humans whether it's a 1 or a 7, we might get different opinions. Here the neural network says it's a 7, but do we want to rely on the output of a neural network that says it's a 7 when there's a lot of ambiguity between a 1 and a 7? Wouldn't it be better to say this is ambiguous input that we want to exclude? So we want a precondition that says when the input is like this, please don't go on, we are violating a precondition. And this is the most difficult category of invalidity to consider. The third one is tricky. Here it looks valid, it is valid to me, it's an 8, but the neural network says it's a 3 because it has a few pixels that are properly placed that make this an adversarial example. So to me it's valid, then whether it's realistic or not depends on the assumptions that you make. I think adversarial examples make quite unrealistic assumptions on the attack model because the attacker needs access to the input, needs ways to modify it, needs ways to propagate the gradient and decide which are the pixels to be changed to get a misclassification. Good, so validity seems an important notion. It also seems very tricky, very difficult to automate. In the Deep Janus study, we did it manually. We asked humans to tell us if something was valid or not. What about automating the validity check? That would be great. I mean, we would have a precondition, an automated precondition similar to the one that we have in traditional software. There's a couple of works that try to do this. One is ICSE 21, the other is ICSE 20. They both rely on autoencoders. An autoencoder is a neural network that compresses the input into a latent space that contains a few number of neurons, small number of neurons, such that only the important information is kept, the rest is removed. And then you have the second part of the network, which is the decoder, that tries to reconstruct the input from the latent space. This network minimizes the reconstruction error. So these approaches apply autoencoders, train autoencoders on the same training set that is used for the neural network under test. Then, when the reconstruction error for an input is small, what we can conclude is that the new input that we are processing with the neural network is probably similar to the training set. So we consider it as valid. Of course, here we have to be careful. This is autoencoder validity, it's not human validity. The two things might be different. But according to these automated approaches, if the reconstruction error for an input is low, it's a valid input. If it is high, above some threshold, then it's invalid. Then the point is, how do we determine this threshold? And here the two papers, the two approaches differ. In one case, they assume the availability of an anomaly set, and they take the intersection between the distribution of the reconstruction errors in the nominal and in the anomaly set. In the second approach, they do probability distribution fitting, and they choose a threshold that ensures a low false positive rate. But apart from that, the intuition is basically the same. When the reconstruction error is high, we consider the input as not valid. And as a side note of the first paper, they observed that some said that some test generators that are widely known, well known, produce a significant number of invalid inputs. So given this possibility of automating validity check, and given the number of input generators that are available, what we considered was to compare test generators for validity. So the question that we wanted to answer empirically was whether existing families of test generators produce valid or invalid inputs according to the autoencoder validity, which is an automated way to assess validity, according to human validity, which eventually is the ground truth. We want to compare the automated and the human validity, and we also wanted to check label preservation. What is label preservation? Well, most test generators make the assumption that when you manipulate an input to produce a new one, the label is preserved along the process, which is key to have the oracle, because if you don't have the label, you don't know whether the input is misclassified or mispredicted when you apply it to a neural network. So label preservation is an implicit assumption that is always made by these test generators. Since in the human validity study we collected also labels, we could also measure label preservation. So the paper was presented yesterday by Vincenzo in this conference. I will not repeat his presentation. It was great. I will just summarize some conclusions. So what we found is that there's a lot of invalid inputs. We confirmed that there's a lot of invalid inputs that are generated by test generators. So again, a pitfall or a warning. Validity is important to consider when you create a new test generator. And then depending on the family, if it is a raw input generator, then invalidity is due to the amount of corruptions that you have on the input. If it's a latent space-based generator, then the invalidity depends on the lack of continuity in the latent space. The quality of the model affects model-based generators. And for all generators, what we also discovered is that label preservation is not ensured. There's a non-negligible portion of the inputs for which the label should have changed. Good, so let's assume that we can generate inputs that cause mispredictions. Then we want to use them to improve the network. We want to use them to retrain the network. But we know from the previous empirical study that we cannot rely on the labels. So what we typically have is an active set of new inputs that are possibly generated automatically. And what we want to do is we want to prioritize them for manual labeling. Before they are inserted into the training set, we have to validate them. We have to check that they are valid, because we know that a substantial fraction of the inputs might be invalid. They might be ambiguous, which is anyway difficult to catch even for autoencoders. And we want to check manually if the label is actually preserved. Typically, the techniques that generate misbehaving inputs produce a huge number of inputs. So what we want to do is we want to prioritize them. How can we do that? Well, we investigated one technique, which is based on uncertainty estimation. The intuition is that when a model, when a neural network is uncertain about a given prediction on an input, then that input is important for that neural network, and we should give that input high priority. How can we estimate uncertainty? Well, there are several techniques, several families of techniques that are available from the literature. The simplest ones are in the family of the vanilla softmax. They just rely on the output, the softmax output layer of a classifier, if we have a classifier, so they are applicable only to classifiers. And they look at either the entropy of the distribution in the output or the difference between the maximum and the second output. But they are pretty simple to apply. The second category is called Monte Carlo dropout. It's based on the idea that you can introduce a dropout layer that introduces randomness in the neural network by dropping some of the outputs of some neurons randomly. This is useful in the training process to increase the capability of the model of generalizing, but what we can do is we can activate dropout layers at inference time, at testing time. If we do this, the output of a neural network is no more deterministic. So if you take a trained network, you apply an input, you get a single output, or everything is deterministic. If you enable the dropout layer, which typically you don't want to, but if you do that, you get, every time you do a prediction, you get a different output. Then what you can do is you can measure the variance, the standard deviation of the predictions, and if that's high, you can infer that there's high uncertainty. The third approach, deep ensembles, work in a similar way, but it uses multiple models that are trained, the same model that is trained multiple times, so multiple instances of the same model. Each of them will give a slightly different prediction. The variance of the predictions give you uncertainty. So all these techniques are available in a tool developed by Precrime, which is called Uncertainty Wizard. You can easily get it, pip install Uncertainty Wizard. It's very well documented. It has a lot of examples. It's designed to be, easily usable with minimum impact on the given source code. It's very transparent, so please check it out if you are interested. Once we have an estimation of uncertainty, then we can prioritize the inputs and decide which of them are important for improving the neural network. And then we can compare different orderings using metrics like APFD, the average percentage of faults detected, and we can see on the right that if we use uncertainty, we prioritize first the inputs on which we have higher uncertainty, which happens to be the ones that expose more failures. Here again, there's a warning. When I say more failures, there's the problem of the uniqueness of failures. If you look at the first two failures, they don't look really distinct ones. So here we should also apply feature maps to make sure that we are counting failures properly. Which again is one of the pitfalls that can be found in the literature and should be avoided. So we talked about faults, we talked about inputs. The takeaway messages that I want to leave you about inputs is that it's easy to generate inputs that fool a neural network, but it's not easy to ensure that they are valid, and it's not easy to ensure that they have a valid label. If you want to prioritize uncertainty, it's a good tool to do it, but be careful about traditional existing metrics like APFD because they should take into account diversity. The third element of the testing framework is oracles. We talked about the accuracy as a probabilistic kind of contract that we stipulate at the model level, at the low level with the neural network. Here you see the previous example. The semaphore is classified as not red, which may or may not be a contract violation, but what's more interesting for us is what happens at the system level. So the system level oracles are the ones that we care the most. So of course, if you are a machine learning engineer, you care more about accuracy, that's what you want to increase, but what we care is system level oracles. So let's take the example of the red semaphore. So we have a self-driving car, and we get this image that is classified as not red. Is this a problem at the system level? Well, it depends, because this is a single frame. Maybe here the image is taken in a position or in a lighting condition that is difficult, but maybe on the next frame the classification is correct. So the car can stop at the semaphore and nothing bad happens. So a single misclassification in a stream of data does not necessarily imply a system-level oracle violation. While if you have a repeated sequence of them, then that could be more troublesome. So at the system level, if we want to define oracles, we need quality indicators. So number of traffic sign violations can be one, the lateral position of a self-driving car, the headway position. Here you see a number of possible metrics that can be introduced to have system-level quality indicators. Then, of course, if you have these indicators, one problem is how do we set a threshold? When is a system-level oracle actually violated? And so ideally you want the metrics to be below the threshold, but at the same time you want that they are below the threshold when everything is fine in nominal conditions, but you want the thresholds not to be too high. They must be low enough to be able to catch faults. How can we simulate those faults? Well, we have deep crime, we can inject them. So our formulation of the threshold selection problem is let's find thresholds that are low, that are big enough to not trigger false alarms in nominal conditions, but that are small enough to trigger an alarm when we are executing a mutant. So this is a possible way to define system oracles for a system that contains deep learning components. Still, we know that the kind of warranties that we have are probabilistic, which means that at the system level there is some remaining probability of an oracle violation. So we cannot assume that at runtime everything will go fine, and what we can do is we can have a runtime oracle as well. So we can monitor the execution of a system through a supervisor, and whenever something unexpected is detected, we can disengage the neural network, the deep learning component. And then we can recognize unexpected conditions, which, if you think about it, is the initial vision of the pre-crime project. Using autoencoders, this is a black box way to recognize unexpected conditions. Here you see an example. If the road is familiar, it's reconstructed faithfully, so the reconstruction error is small. But on the bottom left, you see a case of an unfamiliar road. The reconstruction error is high, and then probably we want to disengage the autonomous driving pilot in the car. The other way to have a runtime oracle is a white box one. So instead of looking just at the input and recognizing unexpected ones, we can look at the model. Is the model sure, confident about the prediction, or is the model uncertain? And here I don't have to repeat myself. We can use several techniques to do uncertainty estimation. So for the oracles, the message I want to give you is we have to focus on this at the system level, because that's our unique contribution. We are not machine learners. We are not focusing just on getting the highest possible accuracy. Our focus is getting a system that works. And we have some ideas on how to get thresholds at the system level, but most importantly, whatever threshold you choose, whatever oracle you choose, there is some residual probability of a system-level failure, which requires runtime monitor and runtime oracles. Good, so we are close to the end. I think I touched all the elements of the framework, except that we said Boolean correctness does not hold. We need something statistical, like system reliability. If we want to have that measure, which is quite important at the system level, then there's an important aspect to take into account, which is the development to production data shift. So whatever measure of reliability you get on the test data, you probably will experience a lower reliability on the production data. So it's quite important when we move from the test lab to the production to collect production data and to estimate reliability on such production data. With this, the framework, I think, is complete from my point of view, and we can restate the goal of testing for deep learning components. It's repair faults exposed by choosing inputs whose execution violates oracles to increase the reliability measured in production. And this has some implications. So we already commented that 100% accuracy or reliability is unrealistic. This means if we want to know the exact or if we want to estimate reliability, we need to collect or simulate production data. We need also techniques to estimate reliability in a sample-efficient way, because we probably cannot afford too much sampling of production data. The eventual metric to decide if a new deep learning testing technique is effective or not should be reliability increase measured on production data. This is something that no paper published so far did. It's really in the future, hopefully. It's a level, it's a bar that none of us achieved, including all my papers, of course. On the last but one point, there's an interesting paper at ICSE 21 you might look at that makes a proposal for the efficient estimation of reliability. So let's put everything together in the final framework. So we discussed deep learning faults, and what I tried to tell you was that they affect the data that we use for training, the architecture, the hyperparameters, the process, not just the code. Then we talked about failures and how important it is to take diversity and uniqueness into account when counting them. We talked about input generation and how difficult it is to ensure their validity and how difficult it is to assign them a valid label. We talked about the oracles and the system-level oracles, and we talked also about the importance of runtime supervisors for neural networks. And the final part was about estimation of reliability and overall assessment of a deep learning testing technique, which I stated again as the effectiveness eventually should be measured as reliability increase on production data. And with this, I'm done. I thank you for your attention, and I'm ready to take questions.
Okay, so the floor is open for questions.
Thank you for a really comprehensive survey for people who aren't experts. It was a great introduction. But one question that nags at my mind is reliability is less important than risk, and that the risk is the multiplication of reliability by consequence. Yeah. So what do we do about minimizing risk rather than just getting reliability?
Yeah, it's a great point. I think that's where we want to aim at eventually, because it's not just a matter of estimating a single number, which is the probability of a failure, but we also want to know the consequences of those failures. You are sort of raising the bar even more. So as I said, reliability estimation is still not at reach of our current approaches. Risk estimation is even beyond, even more far away. But I definitely agree. If we want to see the road ahead, then risk assessment is definitely there. It's definitely important. Thank you.
Hello, Paolo. Thanks for the great talk. I'm Jie Zhang from King's College London, and thank you very much for so many great work in this domain. So my question is about the test oracle problem. You mentioned the importance of reliability, the importance of using in production data set. But I feel that as long as the data set is fixed, we still have the three problems of using the test set, which is the first problem is the adequacy problem. It may not represent the distribution of the whole data set, right? The second one is the distribution shift, because in future the data may shift again. The third problem, which I think probably is the most important problem in my opinion, is the overfit problem, which means that as long as we fix the data set, when we try to repair the fault, for example, when we tune the parameter, we will check the accuracy on the test set. If the accuracy is lower than the threshold, we will go back to change again, then check the accuracy again. So in this process, the data set is in the loop, right? So as long as, although it's not used in the training data, it's still in the loop, so it's still overfitting, and we can call that test set overfitting. Yeah. So I guess it's not just a problem for fixing deep learning faults, it's a problem for any model building problem. So I wonder what your insights on this. Thank you very much.
Yeah, no, it's a very good point. It's difficult to get production data. It's difficult to get reliable information on the production data shift. What could be done in practice, what we are starting to do now is to simulate the production data shift. So basically, when we start the empirical investigation, what we do is we also collect an evaluation set, which is different from the test set, and that includes some production data shift that for now is just simulated because we don't have access typically to real production data. And then we do all the standard assessment with the test set in the loop as you described it, but then we also do the extra step of taking this data set that we put apart, that we put aside, and check what happens if we simulate a production data shift. Then the other point that you make is also very interesting because this production data shift is not there once for all. Well, of course, it depends on the domain. So maybe on some domains, you take a network trained on some data and then you apply it in a slightly different domain and the domain remains stable over time. But you're right, there are domains in which the data shift is not always the same, the distribution changes. And this, I think, is potentially another interesting research direction. So how can we monitor this data shift over time as we are in production, and how can we reevaluate the performance on that, and how can we go back to the loop, to the optimization loop if something goes below some threshold or is unsatisfactory. So yeah, thank you, good point.
I like your points very much, thank you.
Hello, Jingyue Li from Norwegian University of Science and Technology. My question is more general and not very technical. I'm very impressed by how many papers you can manage to publish this AI stuff into the software engineering conference, because I feel that the AI for ICE is very popular in this community, but ICE for AI is quite difficult to get paper accepted. Because it looks like we use different terms. Here you talk about repairing. In the AI domain, they just simply use fine-tuning, right? And when you talk about test oracle in AI domain, they call it robustness measurement. Or when you talk about mutation test in the AI, they call it adversary perturbation or natural perturbation. So my question is that if we want to publish this AI intensive technologies into the ICE conference, should we change the term to make it understandable by this community, or should we increase the number of experts in the community to know more about the AI terms so that they really understand the importance of the problem we are addressing?
Yeah, thanks. I think it's a very interesting observation, and the two communities have a different perspective on the problem, of course. So some problems are common, but the perspective is different. We are more at the system level. So some of the kind of testing that we do are not so much important for them, and vice versa, but there's a substantial overlap. So ideally, I think we should be aware of their terminology, and possibly they should be aware of ours, and we should use the terminology consistently. Also, we should be aware of the algorithms and the techniques that are developed elsewhere, not to reinvent the wheel. It's not easy because they are two large communities and it's difficult to be in sync with both. I think we have made some important progress in this, because if you look at papers that are published in this domain, in deep learning testing, they have become increasingly more mature and aware of what's in the other community. But I agree, it's not easy to catch up and be consistent.
Yeah, so my follow-up question.
Yep.
So if you publish paper, how to decide if I should submit paper to the AI conference and if I should submit to the ICE conference?
That's a very good question. I mean, being also a program chair for some conferences in our field, it's one point that pops up often with papers in deep learning testing. So is it in the scope of this conference, or is it better suited for the other one? So to me, if there is a software engineering contribution that looks at the system level performance, that don't just try to improve the model in isolation or the algorithm to train the model, then it's in the scope. But I agree the decision is quite tricky. Some papers could be published in both, and we had some papers that are published in the other conferences in the DML community that are very relevant for ours and that basically address our problems. So yeah, it's a good point.
Okay, thank you.
Thank you for the inspiring talk. Most of the talk was on testing a single neural network, whereas today we have this complex deep learning system with composition of many neural networks, and composition could happen at the pre-training, at the fine-tuning, or even at the operation phases. So have you looked at the kind of fault that could be related to composition and how to test these complex neural network systems?
Yeah, so short answer is no, but I agree these are important and more prevalent examples that we will have to look at, and it makes the thing. So as you have seen in my keynote, the problem is already quite complicated, but in these cases where when you have fine-tuning and possibly also small step tuning at runtime, the testing problem becomes even more difficult. So these are challenges and opportunities, I think, for us to think about what it means to test these systems. Thank you.
Thank you for your highly interesting talk. I'd like to raise the issue of scalability and get your comments on that. Let me take two examples from your talk. In one case, you do test input prioritization by executing the model and looking at the uncertainty of the output. Another example is that you create mutant models that you have to retrain. Mm-hmm. So what that means in practical context is that you have to prioritize inputs by executing them first, which creates all kind of practical and scalability issues in practice, because you would like to prioritize inputs before you execute them, although on very large models, for example, or worse, on AI systems, you know. And same thing for mutants. If you want to use mutants to assess a test suite, then generating thousands of mutants that you have to retrain is just not a possibility in terms of scalability, especially for the increasingly large system or models that we have to deal with in practice. So I'd like to get your perspectives on scalability of the research solutions that we propose. Thank you. Yeah, no, it's a very good point. So about prioritization, the context in which I presented prioritization was that of the manual effort of labeling and checking the validity. So in that context, I think executing the model is acceptable. But you are right, there are other contexts in which that's not affordable, especially if you have large models. Then we have to find something else. We are not yet there. And your second point was about, mutation analysis. Yes, now it's very expensive. We are looking into it. The problem that we found, so we have some preliminary results. We compared pre-training and post-training mutation, and pre-training is much better. It's much more capable of this. I didn't present the results, but we have quantitative results. It's much more capable of discriminating good from bad test suites than post-training mutation operators. So what is post-training mutation? It means that you randomly add noise to the weights, to the weights of a trained model. If you do that, you are often disruptive and get mutation operators that are not very good at exposing failures effectively. But what we are trying to do is investigating smarter post-training mutation operators that either correlate with the pre-training ones or can be given some more semantics than just randomly changing things. But it's an important problem. So we have definitely to go beyond pre-training mutation if we want to scale. I agree. Thank you very much.
Thank you very much for a very nice talk. My question is related to adoption of related tools and techniques at the hands of practitioners. Supposedly, especially for like the problem around DR model, because the interface is simple and the technologies or techniques are supposedly, I mean, not too much between the practical setting and the like research setting. It should be a golden opportunity, right, for these areas, tools and techniques being adopted by people, especially now. Deep learning models, of course, I mean, still important despite like the emergence of the large language model. I mean, by itself, it's still deep learning, like by nature. But what happened? Because like your slides or your talk did not talk much about what's going on. Like for these great tools, techniques, would practitioners adopt it? If not, why not? How we can go there? Thank you.
Yeah. No, it's a very good point. Of course, adoption is always difficult. We know in our community so that this transfer to the industry is a difficult step. First, I want to say that there is evidence that some of these techniques are being developed internally. We don't know with how much influence from us, but definitely they are. One notable example is runtime oracles and supervisors. I mean, Tesla is developing them, and if you run the autopilot mode in a Tesla, it sometimes disengage because it cannot go on. So these ideas are in production. The problem is that these companies are very protective. So talking about Tesla, they have a fantastic simulator of self-driving cars, but nobody has any clue of what's inside it. So you are right. I mean, technology transfer is important, but especially in safety-critical domains, it's very challenging. So I'm sorry I don't have an answer to this, but I agree with you that at some point some kind of discussion, collaboration, confrontation would be very useful and important. Sorry, no answer.
Thank you for a great talk. Quick questions. Currently, I study DNN repair technique for coping with long-tail distribution in the open world. I try to use your deep Hyperion techniques and current generative AI, such as Stable Diffusion, but it's still difficult to generate rare cases and only at the part of tail class. So how can I generate such tail class before production? If it's possible, I want to know your comments. Please. Yeah,
I'm not completely sure I got your question. What I can comment is that Hyperion, which is the tool behind the creation of feature maps, has a number of limitations, which we know, and we are working on them. So in particular, we need a way to quantify features and to manually define features to make them measurable, which might be tricky, and we are working on the automation of that part. So if you are working on complex domains where getting features, meaningful features is difficult, then yes, I agree, we are not yet there with our tool, but we are working on it. You will see more news coming, hopefully, in the next months.
Okay, let's thank Paolo.